Hello everyone, welcome to the lecture 27 in the course Diffusion in Solids. So far when we have talked about the interdiffusion, we have only told that the diffusion equation becomes complex, and then we started also looking at more the driving force for the diffusion, how the phases form in the interdiffusion zone, how to draw the concentration profiles, without actually going into the mathematical formulation or understanding of the diffusion equation in the interdiffusion scenario. So, as I said that although that forms not really a major objective of this course, but still it is worth to look at least one of the methods to see how the mathematical treatment is done when we want to solve the interdiffusion equation. So, I will just take one example which is for this lecture, and then we will continue with further interdiffusion related topics in the next lecture. So, this analysis is known as the Matano-Boltzmann analysis. See, what happens is we know that so far earlier also we have derived diffusion couple equation using error function analysis. The solution contained error function, but there we consider diffusion coefficient as constant. If you remember, we said that the concentration of B should be small, the gradient should not be large, and the value of diffusion coefficient of B should be sufficiently higher than A. This is mainly used for analyzing the interstitial diffusion, since there the interstitial atom diffuses at much faster rate than the parent atom. In reality, particularly for substitutional diffusion, there is a diffusion change in diffusion coefficient with respect to concentration, and therefore the error function cannot be used. If error function cannot be used and diffusion coefficient depends on the temperature, how do we solve? Because the problem is that dou C by dou T we have written, the fixed second law is equal to dou by dou x of d tilde into dou C by dou x. Now, if I can't take this d tilde out, if it is dependent on concentration, then I have to apply the product rule, and therefore I have to write d tilde dou square C by dou x square plus d by dc of d tilde into dou C by dou x whole square. This particular term is what makes this equation inhomogeneous, and there is no easier way to solve this. So, what do we do now? So, let us consider two alloys of initial concentration Cb minus and Cb plus, which form a diffusion couple and annealed for a time t. And assuming the diffusion couple to be infinite, let me just show you the sketch. So, this is the situation, Cb minus and Cb plus. This is the initial condition, and as the time progresses, the interdiffusion zone which is here expands. But we assume the diffusion couple to be infinite, so there is always certain portion which remains unaffected. So, the initial conditions are that Cb is equal to Cb minus for any x less than 0 at t equal to 0, Cb is equal to Cb plus for x greater than 0 at t is equal to 0. Now, this minus and plus represent left hand side and the right hand side of the diffusion couple. So, what Boltzmann suggested is that we take a variable or we take a parameter like a lambda, which is dependent on only the composition, and it is defined as x minus x naught by root t. Now, what is this x naught? X naught is a initial contact plane, also known as the Matano plane. It is this initial contact plane. Now, you may say that what is so hard to find this initial contact plane? If you remember the images that we have seen in the interdiffusion zone. So, it is this interface is only visible in a micrograph only at the beginning. After the diffusion has taken place, you don't know, actually you cannot separate out where the initial contact plane was located. Nonetheless, right now for the mathematical analysis, what we are saying is that x naught is the initial contact plane with respect to which this Boltzmann parameter is defined. So lambda is equal to x minus x naught by root t. So remember here the x is the distance measured from the Matano plane. Now this equation suggests that for every concentration Cb star, which is let's say composition of interest or any composition, will move from initial contact plane such that lambda star is equal to x star by root t will have a fixed value. Means that x1 by root t1 is equal to x2 by root t2 is equal to constant. So you see here, for example, or here also I have shown that if you have x naught, which is the initial contact plane, so if you have a composition Cb star, which is after a time t1 located here at a distance of x1, if you do the annealing t2, you will get Cb star at another x2. So x1 by root t1 is equal to x2 by root t2, and that parameter is actually known as lambda. And this is a characteristic of a diffusion controlled interdiffusion growth. So this is what is some kind of a physical meaning for the Boltzmann parameter. Now, how do we go about it? Just now we have only defined the Boltzmann parameter. Now, how do we use it? So we know that dou Cb by dou t is equal to dou by dou x d tilde dou Cb by dou x. We are still assuming a diffusion in one dimension, which is the x. Now let us call it as equation 2. Now taking x naught as origin, so x naught is our origin now. So x naught we take as 0. Any x that we measure is with respect to x naught. So therefore the lambda is equal to x by root t. If lambda is equal to x by root t, then dou lambda by dou x is 1 by root t. So we are only differentiating with respect to x, which is 1 here. So 1 by root t. What is dou lambda by dou t? That will be equal to minus x by 2 t to the power 3 by 2. Remember, differentiation of x to the power n is n times x power n minus 1. So here it was minus half, it becomes t power 3 by 2 in the denominator. Now if you put these values, or rather before that, let us calculate dou Cb by dou t. Now dou Cb by dou t, if you use the chain rule, you can write it as dou Cb by dou lambda into dou lambda by dou t. Now we just now saw the value of dou lambda by dou t. So therefore dou Cb by dou t can be written as minus x by 2 t to the power 3 by 2 into dou Cb by dou lambda. Let us call this equation 3. Similarly, you can write dou Cb by dou x, as dou Cb by dou lambda into dou lambda by dou x, which will be equal to dou lambda by dou x is 1 by root t into dou Cb by dou lambda. Now from 2, 3 and 4. So you put this value of dou Cb by dou t here and dou Cb by dou x here. So what you get? What you get is minus x by 2 t to the power 3 by 2 dou Cb by dou lambda is equal to dou by dou x of d tilde into 1 by root t into dou Cb by dou lambda. Now what do we do with this x? Again we substitute dou by dou x as dou by dou lambda into dou lambda by dou x. So again dou lambda by dou x I should write as 1 by root t, and here if I write 1 by root t, here it is t power 3 by here there is 1 by root t. So root t into root t comes out. Remember, this is only differential in lambda. So what I have is minus x by 2 t to the power 3 by 2 into dou Cb by dou lambda is equal to 1 by t times dou by dou lambda into d tilde dou Cb by dou lambda. Now you see that t and t power 3 by 2, they will you can divide, and you get minus x by 2 root t dou Cb by dou lambda is equal to dou by dou lambda into of d tilde into dou Cb by dou lambda. Now, actually, now I can actually write it as simply d, because Cb lambda is only a function of Cb, which I will do later. So, if I now write x by root t as lambda, I can write minus lambda by 2 into dou Cb by dou lambda is equal to dou by dou lambda of d tilde into dou Cb by dou lambda. So, you see that what the Boltzmann transformation has done is brought the complete equation into the terms of Cb and lambda. Now, I can multiply here by both sides by d lambda, and what I get is minus 1 by 2 lambda dCb is equal to d of, remember this is a differential, so d by dx, so this is d of d tilde into dCb by d lambda. Now, when I want to integrate both the sides, remember that x is equal to plus minus infinity, lambda is also equal to plus minus infinity. When lambda is minus infinity, that means one side of the n members, then Cb is equal to Cb minus. When lambda is equal to plus infinity, then Cb is equal to Cb plus. Now, what I can do is integrate, and I can put lambda times dCb from Cb minus to Cb star is equal to Cb minus to Cb star d of d tilde dot d tilde into dCb by d lambda. Now, this Cb star is basically the composition of our interest. Basically, see, one thing is what is slightly different in this analysis compared to previous solutions of diffusion equations that we did is here it is not possible for us to determine the variation of Cb. So, what we are trying to determine here is how the interdiffusion coefficient itself changes with the composition. So, with this Matano-Boltzmann analysis, we will be able to derive the variation of d tilde as a function of composition. So, therefore, what we are interested in is finding out d tilde at a certain value of composition, let us say Cb star. Now, Cb minus 2 Cb star we do, this is this is the left hand side lambda dCb, the integral of the differential is the function itself. So, this becomes d tilde into dCb by d lambda from at Cb star minus d tilde into dCb by d lambda at Cb minus. Now, dCb by d lambda at Cb minus will be equal to 0. So, you can see actually the profile here carefully once more. So, you see here that this profile, the Cb profile actually becomes horizontal, because there is this is an infinite diffusion couple. So, we assume that there is no diffusion that is happening till the end. So, you can see very clearly this becomes horizontal, which means that the slope is 0. So, therefore, I can write that dCb by d lambda at Cb minus is equal to 0. And therefore, we can have minus 1 by 2 integral Cb minus to Cb star into lambda dCb is equal to d tilde into dCb by d lambda at Cb star. Now, if you substitute lambda is equal to x by root t again, so you have x by root t will be out into dCb from Cb minus to Cb star is equal to root t into d tilde into dCb by dx by at Cb star. Now, therefore, the rearranging, if you do this, root t into root t becomes t. So, d tilde Cb is equal to minus 1 by 2t, and in the denominator you also have dCb by dx at Cb star is equal to x into dCb from Cb minus to Cb star. Is it clear? So, this is the expression for the interdiffusion coefficient. Now, usually it is easier if our integration variable is x instead of c. So we can make some slight changes here. So to convert this integration variable to x, what we do is we use integration by parts. So you have here x into CB minus CB star minus infinity to x star. X star is basically the location where CB star exists. So because CB star is a composition of our interest, it is located at a position x star. So this is CB minus to CB star minus infinity to x star, again into differential of x is dx. Now here we can write this as minus 1 by 2t dou CB by dou x at CB star. In the bracket in numerator, you will have x star CB star minus CB minus infinity to infinity integral CB minus CB minus into dx. So this there is a small correction. Now you see here I have represented this composition profile graphically here, and if you see, because you may be thinking this is still looks very complicated, integral to evolve, how will we solve and so on. So you see here, for example, if you this is the schematic of the composition profile. So this is CB minus here, this is CB plus, this is the CB star. Okay. Now CB star is located at a distance x star. So this is at a position x star. Now what is this term? X star into CB star minus CB minus is nothing but this area S. Okay, x star, basically x naught is 0. So this is the distance x star into CB star minus CB minus. So this is the area of this rectangle basically. So this is the area S. And similarly, minus infinity to x star integral of CB minus CB minus is nothing but this area R. So basically what you are having is the integral, this integral is the area under the curve, so area represented by the curve S plus area represented by the curve R. This divided by 2t in dCB by dx at CB star gives you the interdiffusion coefficient. Now you may ask how do we actually in practice calculate this? So what you get is a composition profile from your SEM, and then you have the value for different x, you have different composition. So you can use certain mathematical softwares like Origin and so on. You can also write a code for yourself to calculate this value at different compositions. You can determine the d tilde. So this is how this can be understood graphically, S plus R in divided by this. Now still there is one thing that we have not addressed, is how do I find x naught? Remember again I told that once you have, so it is also briefly indicated here, that once you have the interdiffusion taking place, it is not easy to find microscopically where is my initial contact plane. You cannot find, in most of the cases you cannot find it. Then what do I do? So mathematically I can try to find out the value of the initial contact plane. How do I do that? So that can be done if I invoke the criteria of the mass balance. So what I do is, see my mass balance, maybe I will show you this profile again here. So you see here initially CB minus and CB plus, B has a higher concentration here, and the diffusion is occurring from this right hand side to the left hand side. So the gain of B, whatever the B is coming to this left hand side, on the left hand side, is equal to the loss of B on the right hand side. That means across the Matano plane, whatever has across the initial contact plane, whatever the B was there, which came to the other side. So loss is equal to the gain. We assume that there was no evaporation or no new reaction that happened. So therefore, graphically you can see that this loss is represented by this area Q, the gain is represented by this area B, and that area P is equal to the area Q. Okay. So that areas, if we can equate, this will give us the value of the x naught. So because the area P, you see here, this is the area P, this can be written as minus infinity to x naught CB minus CB minus into dx is equal to x naught to infinity CB plus minus CB into dx. So that will give us the value of the initial contact plane. So you can basically equate this area P and Q. One important assumption that is done in the Matano-Boltzmann analysis is the change in partial molar volume with composition is assumed to follow an ideal behavior. That means you have A and B, they will start diffusing into each other. There will be change in the volume as B and A intermix into each other. Now, if there is an ideal solid solution kind of a behavior, then because there is no preferred interaction, it will simply follow an ideal increase in the volume. That means according to the Vegard's law, it will increase. It's an ideal behavior, which means, in other simple terms, it means that you have the interdiffusion or you have your diffusion couple, there will be no expansion or shrinkage in the volume of the total diffusion couple. So that is the major assumption it is made in the Matano-Boltzmann analysis. However, in reality, many times the behavior is non-ideal. What happens when the behavior is non-ideal is, when you determine the profile or when you determine the x naught, the Matano plane, using, let's say, the profile of element B, and when you determine the value of x naught using the profile of element A. If it was an ideal case, then both the profiles should ideally give you only one value of x naught, because B and A are related actually. So either you use B or you use A, you should end up in only one initial contact plane. There is only one initial contact plane where A and B were joined. But because of the non-ideality, what happens is that if you calculate x naught using profile of B, you will end up getting a different value. If you calculate using profile of A, you will end up in a different value. In fact, there is a derivation also for this. I have not got into detail of this, but I am just giving you directly the formula. So x naught determined by B profile minus x naught determined using A profile actually is equal to plus minus integral minus infinity to infinity delta Vm by V dx. So change in molar volume, if this is 0, then it will be ideal behavior, and in that case both the x naughts will be equal and the analysis holds good. However, if there is a change in the partial molar volume, then there can be an error introduced in the calculation of x naught. And if there is an error in x naught, then you can imagine that there will be error in d tilde also. So that is the limitation. There are other methods which people have developed where you circumvent the need of determining the x naught. But that is not in the scope of our present course. But what Matano-Boltzmann analysis also gives you are important insights on how to convert this equation to an equation in one variable, and then try to solve the value for d tilde, and then tweaking this a little bit, trying to remove this need for x naught. People have developed further methods to determine d tilde. So with this we will end today's lecture. Thank you.